chemistry classes. So we have done already solid state and equilibrium. This is our third lecture now. Now the today's topic is thermodynamics, which is like more interesting and a topic where the students require more logical understanding. So for these topics, like what we already said, like solid state, equilibrium, chemical and ionic equilibrium, as well as in this topic, like these topics requires more understanding, more knowledge of the student, more application levels we have in these topics. So like what we did already in solid state and equilibrium, here also we will be seeing now or covering this topic through, let us say, some numerical applications or maybe some conceptual applications. We try to revise these topics again, and we'll see this will help you again thermodynamics revision, and hope we try to cover the topics that to the more extent that what we can do, that we will be trying through these numericals. So let us see the first one. An ideal gas is taken from a same initial state P1 to a final pressure, to the same final pressure. We are going in 3 different or 4 different processes what we already see. Like one process is already defined and it's represented already. We are going here from 4 to 1, that is already done. Then there are 3 remaining processes again. Maybe we are going from 4 to 5 there as per the points that are represented here. 4 to 5 we may be moving, or maybe 4 to 2 or 4 to 3. Then based on that we have to answer now things, but already what is again further what is defined in the problem now. So we are going to same final pressure by 3 different processes. Other than that, if it is known that the point 1 is corresponding, means whatever the graph what we are representing here is defining an reversible adiabatic process or adiabatic reversible process, then the point 2 corresponds to a single state or a single stage adiabatic process or a single step adiabatic process. So this process already what we see is a reversible adiabatic process. Then it is defined that from 4 to 2 when we are moving, then it is an first or a single step, means directly we are moving from 2, 4 to 1, then directly, then it is an like a single step. So what is single step meaning? It's nothing but adiabatic irreversible process. So 4 to 1 is adiabatic reversible or reversible adiabatic, and 4 to 2 is an adiabatic irreversible. So the general irreversible process, how you define it, where the pressure from the, let us say the process is we are moving from higher volume to lower volumes now. This process is like what we call it as a compression process. So in this process now, what we already say is suddenly the pressure from the point of compression, means from where we started from here. So we just try to define it, this process, instead of writing the graph like this, we may try to represent it. Suddenly it moves to the upper side and moves to here. So suddenly the process where the pressure from the point of compression where it starts from this volume to this volume, but wherever you come to this stage, the process pressure always remains constant. That is, at an external pressure or a constant external pressure, a single step process is happening. So in such cases, now what is the given option which will be corresponding to this process what we try to define? Okay. So what is adiabatic reversible process is, when if it is an adiabatic reversible process, we say for adiabatic reversible process, PV to the power of gamma is constant. But we can't express this for an irreversible process. That means you say PV power gamma is constant. This is applicable only for reversible process or adiabatic reversible process. But for adiabatic irreversible process, we can't say PV power gamma is constant, because the graph cannot be defined properly. We can't write for any reversible process the graphs. So what we see in this case, like an irreversible and reversible. So if you just see the graph here like this, so what we just use the graphs and try to define the work done and all that. Then what is, we see all the remaining points also here. So let us say the point 3 may be a two-stage adiabatic process, where 4 to 2 is a single step, 4 to 5 will be little bit more multiple steps. How a reversible process can be done? Suddenly increasing the pressures little bit, then compression happens, then again increasing the pressures little bit, compression happens. So all the compression steps, all these compression steps from 4 to 1 is done with an infinitesimally slow steps. So many larger number of steps are involved during this reversible adiabatic process. So it's nothing but like taking the curves like this, taking the points like this, all these points, if you just go on joining them, then it corresponds to now the adiabatic reversible process. So many infinite steps are done, or slowly the process is carried out. So in that case we can use this expression, but not for the adiabatic irreversible. But whatever it is, if it is an adiabatic process, what we usually say, so let us see that here for an adiabatic process. So if a process is adiabatic, there is no exchange of heat between the system and surroundings. So system will not take any heat, or system will not lose any heat. That means your system is suppose kept in a container with a, let us say, now there is a compression or expansion, there is an expandable walls. So you say there is a piston, weightless, frictionless pistons generally. So we have a gas in it, but these walls are completely, means your piston walls and the walls of the vessel are properly insulated, or we call the walls as adiabatic walls. So there is no exchange of heat between system and surroundings, or the gas is our system, means whatever the process where we try to determine the energy changes, that is according to the definition of system and surrounding, whatever the process where we are studying the energy changes is called our system. So there is no heat is flowing, that is we say Q is 0. But according to first law of thermodynamics, we can define this as Q means delta U, according to, let us say, like chemistry convention, we use this way, Q plus W is equal to delta U. This is the general convention what we usually say, but maybe here in physics convention and chemical conventions are little bit different, where we write Q minus W is equal to delta U there. But the basic thing is the work what we define here, W, what we define here is nothing but WE is nothing but minus of P delta V or P dV. Means if you write in a smaller changes, we just usually write this expression like this. What is the general differential expression? What we write is, for any path variables, we generally don't use the differential function directly. We generally write a partial differential variable, that is dou Q plus dou W, because work and heat are path functions, and is equal to du. So when you are integrating them, actually we get the net heat. So when an integration is done, suppose when integration is taken for these partial functions, so we get net heat. For the functions, we don't write delta symbol for the larger when integration is done. So we directly write it as Q plus W is nothing but equal to integration of this is nothing but delta. This is okay, just trying to revise the topics, whatever is required for us. But W we usually say as minus of P dV. So when work is determined, we say work is an expansion of, means there is some energy consumption. When a process is done, some work, or when there is a work is involved, work is done, we usually represent it as minus of P dV. In physics, you will be seeing this as WE is nothing but equal to P dV. Work done is there or not. But whenever work is done, as in a chemical convention, chemistry convention, we use as minus of P dV. That's why whenever you are doing, let's say work is done by the system, there is an expansion, we get the negative work, because during the expansion when a differential is dV, integration when it is done, so that we will get a V1 to V2, and during the expansion V2 is greater than V1. So we generally say this work we will get as a negative. Then work is done by the system. So then we will say work is negative work. But when there is a compression, work is done on the system, then work you will get positive, because final volume is less than initial volume. But when the process is like a reversible or an irreversible, so during the reversible also irreversible adiabatic. So if it is a reversible adiabatic or irreversible adiabatic, since work heat is zero, so we say work is nothing but change in internal energy. That means W is equal to delta U. But if you write work as minus of P delta V is equal to delta U, that means if I write P delta V during the compression, suppose, so if it is a reversible compression, then what we see is P final, that is external pressure. Now it is P2, what we write final external pressure, that will be, because the gas pressure also finally becomes only P2 or external pressure. So V2 minus V1, which is equal to delta U, but this one will be negative during the compression. So we say this will be positive. Clear? So if it is irreversible compression, then also we use the same thing, but only we write the delta U part otherwise. The same thing, work will be PdV only, PdV, but we can't generally do like P delta V. In case of reversible, we integrate it anyhow. But anyhow, work, if you take just a simple expression, work becomes negative, like a positive work, because it is minus of minus will become positive. So that delta U will be positive. So during the reversible and irreversible expansions, both, there is delta U positive. That means internal energy of the system internal energy of the system usually here increases. So in an adiabatic process, since work done is on the system, which is a positive work, the internal energy is increasing. So when we consider now the things in this now, the point 3 may indicate the two-stage adiabatic process. So we are saying this is a single stage, this is a multiple steps. So work always lies between, like a work is more in case of reversible work. So work done reversible magnitude, if you take with respect to work done irreversible. Work done reversible always, reversible always is greater than work done in an irreversible. That's how we generally define the work as a area under the curves. Means if you take, this is a reversible. So if you take the curve area here for a reversible, this is the area totally you can take. So this is the area totally. So it's a work reversible area, adiabatic reversible process. Single stage is like this you can take. So this is the only area that we can say. So if you usually say now this graph area is like this. Work done during this single stage process is less, and multi-step process or more infinite step process is high. So that when a process is done in a 2-stage or a 3-stage, it always lies in between these two. Means work need not be more than this, not less than this. So when it is done in a single stage, it will be lesser. When it is done in a higher, in a more number of steps, it will be maximum. So that work always lies in between these two. So when we consider this is a single step, this is a multiple step, we can't say this 3 can be a 2-stage, because always the work area or area should lie between this and this. It is in between this. Means your point which is done in a 2-stage or a 3-stage or a 4-stage always lies in between 1 and 2. It should lie only between 1 and 2. So this one cannot be correct. So the point 3 will not indicate the adiabatic things. It indicates something else. Then next, the average kinetic energy of the gas is maximum at the point 1. So this is the point 1, which is an adiabatic. Maybe this process or these processes are different, maybe. What we don't know. 1 and 2 only we know. It's an adiabatic reversible. This is adiabatic irreversible. So when we consider now, at this pressure, already final pressures are same for all this. This is the volumes what you see. So this is the volume, this is another volume, this is the volumes. So when the volume is as per the ideal gas equation, PV is equal to nRT, PV is equal to nRT for the fixed amount of gas now. When the final pressures are same, if the volume is more, I can say for that gas, temperature is more. So where the temperature may be more? At 3. So T3 is greater than T2, is greater than T1, is greater than T5. So as the volume is high at the particular pressure, the temperature of the system should be high. So that you can directly say the average kinetic energy always directly proportional to absolute temperature. So it can't be at maximum at point 1. It should be maximum at point 3, not at point 1. So which is also wrong for us. Now, work done by the surroundings in reaching the point 3 will be maximum. But during these two, if we try to understand what is happening and what happens at 3 maybe. This is adiabatic. So whatever the work done, that converts into internal energy. Here also, whatever the work done, that also converts into internal energy. But here work done is little bit less. We compare. So when we consider now these two, the net is work is completely converting into internal energy form. But here what is happening is, if a volume change is there, whatever we are seeing it, that is increasing the temperature. That means what we are seeing is the work done, whatever is there, that should only increase the temperature. But here what you see is internal energy of the system is more than the internal energy here. Means your total work is not only consumed for increasing the temperature. It will be something that is the system has taken some heat from the surroundings. System has taken some heat from the surroundings, means some heat has to flow to increase the temperature up to this. Because if the work energy is only utilized, it may go to 1 or 2, because both these processes are adiabatic processes. So at this stage, means if it is a process is going from 1 to 3, then it should not be. Only the work energy is converted into internal energy. Some other heat is also flowing into it. But anyhow, that is nothing to do for us now for this thing maybe, because work done by the surroundings in reaching the point 3 will be maximum. But if you see this, clear? So what is this is now is nothing but the area under this curve. So what is area under this curve indicates is, this is maximum or minimum when compared to this or this, or when you just try to see these two. This work or the area under the curve always indicates, under the PV graph, indicates always the work done. So this one will always be lesser than this one. This is again lesser than this. But if you go, this will be less. Clear? So as you just compare it, the area under the particular graphs, this graph will be always, or this area under this curve will be lesser than the others. So here the work done is not maximum also. So the only thing that might be left for us is, if the point 4 and 5 lie along the reversible isotherm, then T5 is less than T1. Anyhow, this is already we defined it. T1, T5, all this already defined with respect to the volumes. So if these are isotherm, this graph is an isotherm, reversible isothermal, then this is adiabatic reversible. Adiabatic reversible work is more than isothermal reversible. So under this area covering under this, so isothermal reversible and adiabatic reversible. Clear? So this work is more than this. So this temperature is more than this. Otherwise, already we defined it with respect to volumes. So this is the volume. This is the volume. So volumes are less at this stage. At 5, volume is clear. At this stage, it is 1. So this is anyhow higher than this. So at a defined particular pressures, this temperature should be greater than this. So T5 is less than T1. Done? Okay. So the next. If 4 ideal gas samples of initially at a similar stage, P0, V0 and T0, are allowed to expand double their volumes by 4 different processes. So here the processes are defined by isothermal irreversible process, by reversible process having equation P square into V is constant by reversible adiabatic process, by irreversible adiabatic expansion against a constant external pressure, then which one will be corresponding to them? Clear? So let us see what is each graph try to we write here in this. Isothermal irreversible or isothermal any process, PV should be nothing but equal to constant in that. So PV is constant for an isothermal process. But if you take this process, reversible process having equation P square into V is constant. If you write in terms of that as you define a polytropic process. What is polytropic process or? Polytropic process means PV to the power of X or N is constant. So we define the different processes depending on the PV to the power of X. So why we usually try to define PV to the power of X is a constant? Because volume is always, we say, a dependent variable with respect to pressure and temperature. So volume, power will always affects the process basically. So that is the meaning of writing why the polytropic process is basically defined as PV to the power of X is a constant. So what is we see this one, if you try to write that, if I take the square root, means root of this, constant root will be again a constant anyhow, then PV power root is nothing but P into V to the power of nothing but 1 by 2 or root of V is nothing but again a constant. So when we try to take the graph and area under the graphs, as the X value is changing, then your work again can be defined based on what is work we already defined. What is work is? It's minus of P dV, that is integration of that will give net work. So what is this you can write as? It's a constant, let us say suppose K. So I write K into V power X is into dV. Clear? So K by V to the power of X into dV, that is minus will be there anyhow, that is okay. So that 1 by V to the power of X. So as the value of V, X value becomes, let us say high, the curve becomes steeper. So that the work can be defined with respect to that. Clear? So for isothermal graph, adiabatic process, what we define it. So for isothermal, this is the thing. For adiabatic, we can say, let us say it is a reversible adiabatic. We say the graph is nothing but PV power gamma is constant. So how you try to define this? If it is suppose adiabatic and reversible and adiabatic irreversible, reversible, isothermal reversible expansions are there. Suppose we are starting from the same point, we move to a same final volume. This is suppose isothermal, reversible, but suppose the same process means of same is taken under adiabatic process. The process takes place like this. So this is what we say adiabatic reversible. So when the gamma values are taken, which are generally greater than 1, here it is V to the power of 1, here it is V to the power of gamma. Means as the gamma value is increasing, area under the curves will decrease. Here, as the value of X is increasing, area under the curves will decrease. It becomes a steeper. So if it is, let us say compression, it will be like this. Compression graphs are like this. It's an expansion. but the compression graphs will be reverse. So from here we are going like this. So what we already seen in the previous case, this was an isothermal reversible. This is adiabatic reversible. The compressions. Reverse case will be there. So as the value of x is increasing, the curves become steeper. So what we see here, clear? This is isothermal reversible first process. Second process is reversible by PV, P square into V, which is nothing but this one also. So both are one and same here. This is reversible adiabatic process. Then by reversible adiabatic expansion, already just defined now, adiabatic reversible work will be lesser than adiabatic irreversible work is lesser than adiabatic reversible work. So what do you see? Which one may be? So area under this curve. So if a process is from 1 to 2, if process is 1 to 2, here I to 1, I to 2, I to 3 and I to 4. Area under this 1 to 4 is less. So in which case the work is less. Clear? Here it is V to the power of 1, here it is V to the power of 1 by 2, here V to the power of gamma. For adiabatic you can't define like that, you can compare these two directly. This is more, this is less. So 3 should be, this has to be adiabatic reversible. This will be isothermal reversible. But actually we define irreversible process, suddenly drop will be there. So the sudden drop will be there in case of isothermal. This is like isothermal. So if you try to write, try to see in this. This is isothermal irreversible. And this has to be now, sudden drop will be there also here. It's like adiabatic irreversible. So process 1 indicated by graph 2, because isothermal irreversible. So it is 1 indicates, clear? The isothermal reversible process having this one. So this is reversible, irreversible graph. So this is isothermal irreversible type. So maybe this is, it's isothermal reversible is anyhow not there in this. Isothermal reversible is not there. Isothermal irreversible is only there. So in these two, first and second cases, because the case conditions are different. So this may be isothermal 1 to 2 is like I to 2 is isothermal irreversible. This will be PV to the power of the process, reversible process having equation. So your graph for a reversible process, it's a slow changes. So you can define this graph like this. So for this graph, what we say is, for this graph, what we say is P into V to the power of 1 by 2 is constant. So this will be indicating isothermal irreversible, because isothermal reversible was not there. So this has to be adiabatic reversible. The 1 to 4 has to be adiabatic irreversible. So the first one is indicated by the second reversible process having PV to the power of 1 by 2 constant is indicating 1. Third will be indicated by this 3. Clear? Reversible adiabatic process. Clear? Okay, this is irreversible, no? So work in irreversible, work reversible. Okay, sorry. This is also given different thing now. Adiabatic reversible expansions will be like this. Adiabatic reversible expansion is more steeper, and this is like irreversible graphs. So this is actually irreversible adiabatic. This is adiabatic reversible. Clear? So the magnitude wise. So this is the thing what it indicates. Thing done. Let us see the next thing. Okay. Two rigid adiabatic vessels A and B, which initially contain two gases at two different temperatures, are connected by a pipeline by a valve of negligible volume. The vessel A is containing 2 moles of neon gas and vessel B is containing SO2 gas. Then the volume of A and B vessels at 4, vessels are 4 and 6. So it's a 4-liter vessel, it's a 6-liter vessel. It has neon, this has SO2. This is at 300 Kelvin. This is at 400 Kelvin. And Cp for the gases are given. Then process is adiabatic again, because walls are insulated in the meaning, because the vessels are adiabatic vessels. Then the final pressure in atmospheres, when the valve is opened and at 12 calorie heat is supplied simultaneously to the system maybe. So we are giving some heat to the system, means not from the surrounding, we are giving the heat directly into the system. Means something is kept suddenly in the process, means from the surroundings it is not going. So a 12 calorie heat is supplied externally into that system. So what will happen? Because even though we say the vessels are adiabatic, how you say the heat is flowing? Means we have kept some hot source in the vessels. So means in a neon and SO2 vessels, we kept something and we opened the vessel, means a valve in this. So what should happen totally? There should be a heat transfer, so that finally the temperature of the both systems should be same temperature, they should reach the finally same temperature. So the heat whatever we supplied, the energy whatever we supplied should increase the temperature of neon and the temperature of SO2. Means both these will reach a finally same temperature. Means final temperature of the system has to be the same. So from 400 Kelvin, it will reach at TF, final temperature. From 300 Kelvin, it will reach a final temperature of TF. Both will reach same temperature because of the some heat is given into this. 12 calories of heat is given into this. But gases will diffuse in both the containers. Clear? So whatever the heat we supplied is converted to increase their temperatures. So as we use now, the heat whatever is supplied completely utilized because the gases are ideal gases and they are actually diffusing in both the containers. So what will be the net heat? Whatever is we supplied will increase the net temperatures of both the containers and they reach the finally same. So what is now we see is the total heat supplied is equal to increase in internal energy of neon and SO2. Since temperature increases, the vessels are adiabatic, the gases are diffusing into both the vessels. There is an increase in internal energy due to increase in temperature. So what we see, this total heat that is supplied is nothing but 12 kilocalories, which is nothing but, let us say, in 12,000 calories, which should be equal to the increase in internal energy of neon is nothing but NCV T2 minus T1 for neon plus NCV, because for the two gases CV value is different. So NCV T2 minus T1. But how much heat is there totally now? Let us see. Means what is N values, number of moles of this, what we have totally. So according to this now, if you just see, there will be 2 moles of neon and 3 moles of SO2. But the CP values are given for the gases. But what we are actually using is nothing but CV. Why CV we are using? Why not CP? Because the vessels are rigid vessels. So the volume remains same. So the total heat supplied only increases internal energies. That is why we are writing there internal energy also. So what we have to take now, internal CV values of the gases. So with respect to this, if I suppose take what is CV for this, if CP is 4R, CP minus CV is equal to R. So for this way, CV for the gas is nothing but 3R. Here the CV also for the gas is, CV for the gas is nothing but, it is 2.5 minus R. So it will be nothing but 1.5 R. Subtracting R from it, directly we will get their CV values. So from here now, this is 12,000. Number of moles of neon, this is, let us say, neon, this is of SO2. So for this number of moles is 2, CV is 1.5, otherwise you can write 3/2. R value is set to take as 2. This is final temperature is TF minus initial temperature of neon is 300 plus we have number of moles of SO2 is 300. CV is nothing but 3R we got. So 3 into 2 into TF minus initial temperature is 400. So done. So what is this? It's nothing but 6, 3, 6 TF minus 300 plus this is 9, 18 TF minus 400. So this is 6 plus this 24 TF here. This is 6 into 18. This is 18 into 4. So 18 into 4 will be 237. So 72 plus 24. So 0, 0, 6. This is 9. So 9, 6. That will be the negative on that side. Comes here and becomes plus. So it is 12,000 plus 9,600. So 12,000 plus 96. This is 6, 1, 2. So T final will be from here. What is T final? Just calculate that in terms of Kelvin we get. because we are taking in terms of Kelvin everything, because R is 1.98, otherwise approximately he said to take in that problem itself as 2 calorie per mole per Kelvin. So everything we got in terms of now T final in terms of Kelvin. So that now what is the final pressure? So final pressure will be T F, we know final pressure, final temperature. So it's nothing but as again ideal gas equation using total number of moles. So total moles, R value, T value by V final. But what is that? Gases are spreading in 2 containers when the valve is opened. So the total volume becomes 4 plus 6, that is 10. There is 2 moles of this and 3 moles of this. So total moles are 5. R value has to be taken as 0.08. Temperature you have to substitute here by final volume is 10. So we just suppose do the calculations and substitute that temperature there. We get the what is the final pressure. Clear? Then going to the next now. 2 moles of ideal gas is heated at a constant pressure of 1 atmosphere from 27 degrees centigrade to 127 degrees centigrade. So most of the questions that we will be seeing it in internal means in the thermodynamics is energy calculation, internal energy calculation, heat calculation, work, everything. So that suppose if we use this CV expression and he is asking us to calculate Q and delta U. But what do we generally say? Delta U is equal to nothing but NCV or DU if you use, because we have given the variation of CV with respect to temperature, means it is given in terms of as a function of temperature. So DU is nothing but NCV dt. So that internal energy on integration we will get this. So what is N is 2, that you can take as a constant. CV is given as 20 plus 10 to the power of minus 2 T of dt. Since it's a function of temperature, the temperatures are given from 27 degrees centigrade to 127. So this has to be 300, this is 400. So that delta U will be, what is this? This is overall 2. So integration in this 20 and plus this part. Integration of this 20 is again a constant. You can take 20 outside. Then 1 of dt is nothing but t. So with the limits of 300 and 400. So it's nothing but 20 into T2 minus T1, that is 400 minus 300 plus in this again 10 to the power of minus 2 can take outside. Clear? So what is 10 to the power of minus 2? This is nothing but again t square. So that limits again if you apply it. So it's nothing but 400 square minus, this is nothing but 300 square by 2. So that integration of t dt is t square by 2. Okay. So if you calculate this, so what is this we are getting is, this is 100 into 20,000. This is 400 square, this is 300 square. If you take one of the 10 square common, so it's nothing but this part is 4 into 400, that is 1600. This is nothing but 3 into 300, it's nothing but 900. So it's nothing but 700. because 110 square we have taken outside. Clear? So 10 square in this common 10 square part in this, we just take, I think, getting this, otherwise we do it like this. So it is nothing but 400 into 400 actually minus 300 into 300 by 2. This 100 you are taking suppose outside. In this 100 will go, in this 100 will go. That is what we have done. So this 100 into 10 to the power of minus 2. That is what we try to do, make it 1. So this is 1600, this is 900. So it's nothing but 0, 0, 5 and 2, clear, 2, 5 by 2. So that it becomes now 1, 2, 5, 0. So this overall value is 1, 2, 5, 0. This is nothing but now 2000 into 2. So 2000, 1, 2, 5, 0, 0, 5, 2, clear? Then multiple of 2, clear? So you can make it this value. So what is this? T square 2 nr dt, okay? 400 square minus 300 square, 16, 900, so 25, 2 thing. This is 100, 2000. This is t, integral of t, clear? So t square by 2. So just see the calculation part, just we are missing something maybe. So this is what is the general thing. Next, for calculating the Q, which is nothing but calculating the Q, sorry, what we have done is 1600 minus 900. So this is what we, so this is nothing but 0, 7. That is what we miss. By 2, it's 350. So 2000 and this 350. So 2350. So instead of actually doing it subtraction, we did addition. That's why we are not getting that option. So into 2 times of that, it's 47. So 4700. So this is the values, or this is the value for the internal energy. So what is heat totally now? So what is the total heat now? Q. It's nothing but the process is what we generally define it a constant pressure. You say this Q, P is nothing but enthalpy change. The amount of heat entering into the system or leaving the system at a constant pressure is nothing but defining the enthalpy change of the process. So that QP is nothing but enthalpy change, which is nothing but NCP dt. So enthalpy change can be calculated by the integration of NCP dt. But already we said what is CP? CPM, that is molar heat capacity. CV plus R means you are adding that 8.314 because it is in terms of joules. So the CP expression in terms of this will become 28.314 plus 10 to the power of minus 2 into T. Now the same thing if you repeat it here, means it is delta H is nothing but again 2 integration of this thing, same, instead of 20 now we have 28.314. So it's nothing but 28.314 into 100 directly I write, because it is a constant, integration of 1 into dt is 1 again. So that is 300 and 400 we get, plus this is nothing but again 10 to the power of minus 2 by 2 into 350, like same thing what we are repeating it. So this comes around now. So that it's a higher value. Anyhow, it's already internal energy, we are saying it is 47 from here, 4700 joules from here. So what we say, the heat capacity, it's already Cp, Q, whatever we are getting, it should be more than that. So this has to be the answer. Done. Next. Space we left. The gas expands slowly against a constant variable pressure as P is equal to 1 by V bar, where V is the volume of the gas at each stage of the expansion. During the expansion from volume of 10 liter to 100 liter, the gas undergoes an increase in internal energy of 400. What is the amount of heat absorbed by the gas during the expansion? So what is the net heat we have to calculate? So again, this is internal energy change is given. The PV expression is given, or P and V is a constant, or P is equal to 10 by V, which is given. That means we usually say now the work we have to calculate. So what is your Q will be? So according to first law, Q plus W is equal to delta U. So when you can calculate the work, if you take that work and add or somewhere like that Q delta U minus W, then that will be giving the net heat. So already this is 400 directly given for us, minus what is PdV. So with a variable pressure, when the process is done, so what you generally see is we directly try to integrate that P into dV to get the net work done, but we write it as minus, so that it is minus of this minus will become anyhow, let us say plus here directly. So what is now the limits are 10 and 100. So this is 10, this is 100. But what is this P value given as 10 by V? That means it is nothing but 400 plus with the limits of 10 to 100, 10 by V into dV. But anyhow, the 10 I can take again common or outside, which is a constant, so that it is nothing but 400 plus 10 into 1 by V dV is nothing but ln, or you can write in terms of suppose base 10 logs, I can multiply with 2.303 log V with the limits of, let us say 2.303 we take outside and do the application of limits. So the limits are applied only this stage, that is 10 and 100. Okay. So what is log 10 will be and log 100 are? We know all this. Log 10 will be 1, log 100 is nothing but 2. So this is 2 minus 1, so that it is 1. So that this is 20, but it is given, sorry, it is given in terms of bar and volumes are taken in terms of liters. So what is this values you are getting? This value you are getting in terms of bar liter. So the work is in terms of bar liter. This was in terms of joules. So we have to convert your bar liter values into the joules values. So that because the options are given in terms of joules for us. So what we see, this is 400 plus this is nothing but already, this is 1 we said, it's nothing but 23.03. But we know this thing, 1 bar liter is equal to 100 joules. So 1 bar liter per mole per Kelvin is nothing but 100 joule per mole per Kelvin. So it is 100. So this is nothing but 23. This is 400. So that it comes out now 2703. Done. Next space was given. So this part is it. We make it this. It's an integral of the circle, that is dq by t. That circle is somewhere there. So for the cyclic process, so the integration, when we are surrounding it with the circle, that is indicating the cyclic process. Which of the following statement is incorrect? Delta H naught of vaporization of water liquid is greater than 21 into 373 calories. So this is actually based on what we say Troughton's law. So what we usually say this as the delta H naught of vaporization of any compounds can be given as, so this is, let us say, in terms of Troughton's law as it is, delta S naught of the vaporization of the process is nothing but nearly for all the liquids under the standard condition is equal to 85 calories. So this is indicated by Troughton's law. Standard entropy change during the vaporization of any liquid, means a standard, that is at their boiling points, is nothing but nearly equal to 85 calories. But what is this? You can say this is nothing but delta H naught of vaporization by the TB, that is the boiling point of that liquids. So what is delta H naught of vaporization, sir? Delta H naught of vaporization of water liquid, because the water boiling point is nothing but, we usually say it is 100 degrees centigrade, that is nothing but 373 Kelvin. So that it is nothing but 85 into 373 calories. So this is anyhow higher than this, because it is 85 into 373. So this statement is correct, but what we require is incorrect statements. Okay. Now, the integral of dq by t is 0 for all cyclic processes. But if a process is suppose done from 1 to 2 in a reversible path, but if the process is done from the 2 to 1 in an irreversible manner, that is, overall cyclic process becomes totally the irreversible process. But what is dq by t will give as an on integration is generally, it gives nothing but delta s or ds. But when we just take a cyclic process, when it is completely reversible, it should not be equal to completely. If a process is reversible, delta s reversible process, generally if the process total overall cyclic process is a reversible process, we say it is equal to 0. But delta s of total irreversible cyclic process, so cyclic, reversible, cyclic, irreversible, this should be lesser than 0, because some amount of heat actually lost somewhere. That is what we get a conclusion from the Carnot cycle. And this equation, what we generally say as integral of a cyclic process dq, which is suppose irreversible, can be less than or equal to 0. If it is a reversible process, it becomes equal to 0. For an irreversible process, it becomes less than 0. This is what we also call it as Clausius inequality. So according to Clausius inequality, for all cyclic processes, if 1 to 2, 2 to 1 is suppose both are reversible, since entropy change is a state function, entropy changes are always determined only during the reversible processes. Entropy change for the total cyclic process becomes equal to 0. But if it is completely the process is cyclic process is not completely reversible, means all the steps are not reversible, then the total cyclic process is also not called reversible process. It's one of the process, if it becomes at least irreversible, the total cyclic process also becomes irreversible in nature. So this is not equal to 0 for all cyclic processes. So Clausius inequality proves this statement is not true for all cyclic processes. This statement is wrong. So this is our answer actually, because we need an incorrect statement. So let us see, maybe because in an advanced we may get a 1 or 2 more option type questions. Adiabatic reversible process is an isoentropic process. So directly we can say adiabatic reversible, Q reversible is 0. Therefore, delta S for the process is equal to 0. But how we prove it for a delta S for the process, that is with respect to the system, it is 0. Even isoentropic, system entropy will be 0, surrounding entropy will be 0. Both will become 0. Anyhow, since system is suppose adiabatic, what we usually say, there is no heat is going into the system, so no heat is entering, so delta S surroundings will be 0. Even a process is reversible adiabatic, even a process is irreversible adiabatic, entropy change in the surroundings will be always 0, because surroundings will not gain any heat, surroundings will not lose any heat. So the system entropy, when you try to determine delta S system, how we determine generally? Delta S system we can write, let's say, taking it out this, delta S system is what we usually determine as NCV ln T2 by T1 plus NR ln V2 by V1. But we say according to adiabatic process, T and V. So what is T and V relation is? T into V to the power of gamma minus 1 is constant for an adiabatic process. So if you write this T2 relation or V2 relation in terms of this, so what I say, T2 by T1 should be equal to V1 by V2 to the power of gamma minus 1. So that if I substitute in this, so what it will be? NCV ln V1 by V2, but I suppose write as V2 by V1. So V2 by V1 to the power of gamma minus 1, but it becomes minus because we reverse these variables. So this becomes like a minus. So this becomes a minus. But gamma minus 1 to the power, so that it becomes a gamma minus 1 in this. Plus this is NR ln V2 by V1. But what is CV by gamma minus 1? CV by gamma minus 1 is nothing but equal to nothing but R. So that NR ln V2 by V1, this is plus NR ln V2 by V1, both these are same, they get cancelled, signs are different, therefore delta S system is also equal to 0. Done. So if an adiabatic reversible process is there, the process is isoentropic because system entropy will not change, surrounding entropy will not change. But if a process is irreversible, system entropy changes because you see the difference in that, because we can't use that T into V to the power of gamma minus 1 is constant for an irreversible process. So volume increase is there, suppose expansion is there, irreversible expansion is there adiabatic, then increase in volume, this will be positive, decrease in temperature will be there during the adiabatic expansion. This is T2 by T1. So this part becomes generally negative usually because it is decrease in temperature is there. Here it is an increase in volume. So this is a positive, this is a negative. So that total delta entropy of the system will become positive. So what we say, for an irreversible process, entropy of the universe always increases because surrounding entropy is 0 in this case. Even irreversible, reversibility is 0. For the system, for the reversibility is 0, for irreversibility is positive. So that we say, in this case anyhow, for us, the adiabatic reversible process, the isoentropic process, this statement is true, but anyhow our answer, it's not an our answer. The next, heat exchange at constant volume condition will be an independent of the path. So QV, heat exchange, is nothing but, and a constant volume is nothing but change in internal energy. But internal energy is a state function now. So state functions are not depending on the path that is followed. So the QV is nothing but internal energy change. It's nothing but a state function. So it is not depending on the path, it's a independent of the path. So this statement is also true for us. So that is also not our option. So only for the integral of dq by t, which is less than or equal to 0 according to Clausius inequality, that is what we say is a wrong statement for us. Next. This type of questions during the entropy calculations, what do we usually see? Delta S for the following change, water solid at minus 10 degrees centigrade is converted into 1 atmosphere into water liquid at plus 10 degrees centigrade 1 atmosphere. And Cp for the ice, Cp for water. So usually the process is done at a constant pressure and the latent heat of ice is also given. But whenever we usually try to calculate entropy changes, this thing we should remember. Entropy changes are always determined by considering the process as to be irreversible. So how a water solid at minus 10 degrees centigrade is converted into water liquid at plus 10 degrees centigrade. Means how the process actually usually happens. That is, water solid which is at minus 10 degrees centigrade and 1 atmosphere first actually converts into water solid, means we are increasing the temperature in this process at a constant pressure. So water solid comes to the 0 degree centigrade and 1 atmosphere. Means the process happens in a steps. So all these processes where water solid at minus 10 degrees to water solid at 0 degree centigrade, the system is under the same physical state at a same atmospheric pressure, the process is happening. that is in a reversible path. Slowly the temperature of the system starts increasing, keeping the pressure same, everything same, volume same. Next, the process where solid will convert into liquid at 0 degree centigrade, because 0 degree centigrade is nothing but defined as the melting point of water. So it's a fusion process, so that where solid liquid means solid will convert into liquid at its melting point, and from here the water is from the liquid at 0 degree centigrade, it changes into plus 10 degree centigrade. So this is how a process of water solid at minus 10, 1 atmosphere can be splitted into water liquid at plus 10 degrees centigrade at 1 atmosphere. So what is during this process is happening? Only the temperature changes are there usually, and here there is only change of state. Here there is again temperature changes. So what we say during a particular process, this stage the entropy change is suppose delta S1. At this stage, suppose the delta change, entropy change is delta S2. At this stage, the entropy change is delta S3. So what we say? Total entropy change, total delta S should be delta S1 plus delta S2 plus delta S3. So delta S1 is nothing but, at this stage there is only a temperature change NCP ln T2 by T1 plus delta S2. Here there is only changes in the state. So during the phase changes, the entropy changes can be measured by the enthalpy change of the process. So what is that enthalpy change we call? The solid is converting into liquid. It's nothing but fusion. So delta H fusion by the temperature at which it is happening, plus it's nothing but again NCP ln T2 by T1. Here only the temperature changes at a constant pressure. So what is this when this one is of liquid or water, of water liquid. This one is nothing but of water solid or ice. So we are already given all this statements here. So how much of water is there for us? So usually assuming it is 1 mole, because nothing is mentioned here. So that let us say 1 mole. So it is for 1 mole. Then Cp for the ice is 9. Ln T2 by T1 is nothing but final temperature. Here is 273. Here it is 263. So 273 by 263 plus this delta H fusion is 1440 for the 1 mole by temperature, that is 273, plus this is nothing but again 1 into Cp, that is nothing but 18 into ln T2 by T1 is nothing but again 283, because plus 10 degrees 283 by 273. So this will give now the total entropy change for the process. Done. So this is again the calculations, the ln values we can use. So natural logs or based in logs we can take and do the calculations. Then we get the net entropy change for the process. Done. Now, so this is the space we left. This is an interesting question again. Out of the different state variables here, E, H, G, A and S, the entropy is the only parameter where we can calculate its absolute values by using the third law of thermodynamics. Is usually say, according to the third law of thermodynamics, when you go to minus 273 degrees centigrade, 0 Kelvin, absolute 0, entropy of all systems should become equal to 0. So, the entropy, the absolute entropy values, what we determine at 0 Kelvin should be equal to 0. If it is a perfectly crystalline solids, they become equal to 0. If it is, there is non-perfect crystalline solids or non-perfect solids, for them the entropy changes will not become equal to 0. So, there is some residual entropy if the it's a means it's not a perfect. So, just using the data chart table here, so try to see for which of the following substances there is a residual entropy at 0 Kelvin. But he gave the CP values, standard melting points, enthalpy of fusions, standard entropy at 100 Kelvin it is given. So, how we actually determine the entropy changes totally? Means ds. So, already we said ds is nothing but, we just now go into the next page and see. So, what is ds is nothing but, already said dou q reversible by t. So, integration of that actually gives delta s. But what is dq reversible? You can take it as dq reversible as delta h, or it's nothing but ncp dt by t. So, for a reversible process, dou q reversible, what do you take it as ncp dt? Because always whenever we try to determine any path variables, we try to convert these path variables into some units of, means in some parameters of state variables. So, work done, path, function, we can't integrate it because it is inexact differential, we say. So, we try to determine the net work done by integrating a state variable. So, we write in terms of PdV, then we integrate it. So, similarly, entropy change, now we are calculating dou q reversible by t, that is ncp dt. But as you see, here the Cp values of the compounds are given. But it is 0.35 into t, 0.25 into t, 0.15 into t, 0.45 into t. So, let us assume now, because he is asking the residual entropy may be there for which type of solid, PQRS, at 0 Kelvin. So, let us try to determine the entropy changes between 0 and 100. So, if you try to see entropy change at absolute value of entropy at 100 is given. So, if I can say entropy change, absolute value of entropy at 0, if I get suppose 0, then there is no residual entropy. If I don't get 0, then I will say it is having some residual entropy. So, for that we take Cp value anyhow what we have all there, because anyhow we are trying to determine for 1 mole, let us say. So, there n becomes 1 anyhow, assume it. So, now it is nothing but 0.35, 0.25, 0.15, 0.45. You usually take now this as a constant, some k. So, what we write this expression now as n is 1 for us, then we are trying to take the Cp value as k into t, expression into dt by t. So, your t gets cancelled, and we are saying the limits as we are applying from 0 Kelvin to 100 Kelvin. So, that your entropy changes what we are determining now, what we write is between 0 and 100, you say entropy S naught at 100 minus S naught at 0 should be equal to as delta S. So, your delta S is nothing but this, but K is a constant we can take outside, K into with the limits, let us say 1 into dt, that is T, with the limits 0 and 100. So, what is this now? This is 100 minus 0. So, this is only 100. So, K into 100. is nothing but S naught at 100 and S naught at 0. So let us take now conditions as for P, substance P, solid P. What is that K value for the solid P? And what is S naught value given for the solid P? 0.35, that is 35. So your K value is 0.35, your S naught at 100 is 35. So what is this will be? This is 35 minus S naught is equal to 0.35 into 100. So this is 35, this is 35. So that we will get S naught at 0 as 0. So P doesn't have any residual entropy at 0. But if you take for Q, suppose for Q, what we see? K value is nothing but now what is we have? 0.25. S naught at 100 is 30. So what is this now? It's 30 minus S naught at 0 is equal to point, how much we had? 0.25. 0.25 into 100. So this is 25, this is 30. So S naught at 0 will be 5. So it has some residual entropy at absolute 0. So for R, then again, going back again, this is 20, that is 1.5. So anyhow, usually you can understand now. So this is 20, this is S naught 0, this is 0.15, this is 100. So S naught of again this is also 5. So R is also having residual entropy. Similarly, you can see for S. For S, what you will have? Say taking again, this is 0.45, this is 50. So 50 minus S naught 0 is nothing but 0.45 into 100. So S naught of 0 will be again equal to 5. So all these are having residual entropies. Only P doesn't have a residual entropy at absolute 0. So, sorry. So this is where Q, R, S, all the three have residual entropy. So P only doesn't have the residual entropy. Clear? Done? Now, coming to the next. The entropy change in argon is given to a good approximation by the expression. Calculate the change in entropy, Gibbs free energy, for 1 mole of gas or 1 mole of 1 mole of argon gas when it is heated from 300 to 400 Kelvin at constant pressure. Express the answer with sign and decimal places. Okay, so let us taking this. But we suppose Gibbs free energy change, what we wanted to take from the standard thermodynamic relation. dG is nothing but equal to VdP minus SdT. So it's a basic thermodynamic relation that we use for the free energy changes, but the process is constant pressure, so the dP is 0, so that we can say dG is nothing but equal to minus of S dt. So if we want to calculate the total, then it is integration of this, but S is given, entropy changes are given in terms of as a function of T. So you are writing that, so delta G, this is nothing but minus of 36 plus 20 ln T dt. So what is at this stage? So integration, again taking the separately, 36 dt integration 20 ln T dt as separate with the limits of 300 to 400. So 300 Kelvin and 400 Kelvin. So what is this is nothing but now 36. So take this total thing as minus. So let us say delta G is minus 36 into T with the limits of 300 and 400 plus this is overall minus is there, let us say, then 20. What is ln T dt integration is? It's nothing but T ln T plus T with the limits of again 300 and 400. Done. So taking the up means taking the values there, so we can determine the clear. So it is coming in terms of joules. Clear. So all are taken in terms of that. Then you can calculate the value in terms of. So it is minus of 3600 plus 400 minus this. This is 20. This is 300, 400, ln 400 plus 400, or you can take 400 common. Then this is 1 unit in this minus 300 ln 300 plus 300. Okay. So this will give the value of this in terms of joules anyhow. Exclude the limits, decimal points. So write the nearest integer values. In the numerical part it is applied. Okay. Now, so always let us say any free energy applications or entropy applications are coming. So how you are using those functions, it's a function of some temperature or something when it is mentioned. So how you are usually taking it? Done. Okay, this is the space. This one. For the balanced equations here, enthalpy changes are given because you are having along with the thermodynamics in chemistry, you will also have like a thermochemistry. So we have heat of formation, heat of combustion, heat of neutralization relation, bond energy relations, let us say like heat of solution, heat of dilutions, all such type of questions. But what is basic things in the thermochemistry is, as you try to apply the applications, you try to do all this through the laws of thermochemistry. So there are two laws of thermochemistry, like first law of thermochemistry called Lavoisier-Laplace law. Means if a process is carried out in one direction, if suppose heat is absorbed in this direction, if the process is suppose reversed, in the reverse direction, the same amount of heat will be released. Means if a process in the forward direction becomes endo, in its backward direction, it will be an exo process with the same quantitative values. Means if it is plus 100 here, it will be in the reverse direction minus 100. Means if you reverse the equation, keeping the stoichiometry same, you have to just only change the sign. You have to write the enthalpy change with a different sign. Clear? The next is Hess law of constant heat summation as a second law. Means if a process is done in a single step, but if the same process is done in multiple steps, sum of enthalpy changes in multiple steps will be equal to enthalpy changes in a single step. So we usually calculate all the other things. Let us say what is thermochemistry use is, even a process which is not possible to carry out, we can calculate the enthalpy changes of that particular process. Why we do like that if a process is not happening also? It's the only thing we try to measure the enthalpy changes or energy changes. Thermodynamics we are studying. as far as chemistry conventions, chemistry in, like I say, the energy changes we wanted to use to predict whether the process is a spontaneous process. So based on that energy changes, can we able to define which process is a spontaneous process? So what is the criteria to explain the spontaneity of a process? So even a process which is not possible to carry out, for such type of process also, we can determine the enthalpy changes using the laws of thermochemistry. So that when we usually take the enthalpy changes here and do the applications, that is formation, combustions and all that, that okay, that is basic thing. Let us say we can see later there. So this one N2O5 is this balanced equations. These are the enthalpy changes for them. So 10 moles of N2O5 and 30 moles of O2 gas is taken in a chamber to cause a complete conversion of N2O5 to NO2 and partially reacts with remaining oxygen such that the volume percentage of oxygen in the vessel becomes 50. That is O3 becomes 50. Calculate the overall enthalpy change for that particular process. So all these enthalpy changes are denoted by per mole. Means let us say now, suppose the gas, the reaction is N2O5 reaction. So conversion, already he is saying the N2O5 is completely converted. So how much of this we have? 10. How much of this we have? 30. But this 10 completely converts according to the given condition. So this is also minus 10. So that 20 will be left in here. 20 moles are left. So you are getting this as 20 moles, because for 10 moles you will get 20 according to the stoichiometry. This as 10 moles. But later NO2 plus O2 is giving NO plus O3. So how much of this we had already? 20. How much of this is left? 20. But we don't know, because he is saying partially it is converted. So some amount of this has to go, that is X has to go from here. Similarly, X amount of this will go, because they are reacting again in 1:1 ratio. So that you will get X. Because why we are only taking that is, because you may be, let us say even this you can take X. So here X reacts, you will get X and X. So that the overall changes here will not be there with respect to the initial condition. That is, you have 20 here, we have 20 here, we have 10 moles here. Finally also, in this X reacts, you will get X, you will get X. So that overall total moles again remains same. So what is the overall moles is? Total moles is always, total moles after complete reaction is, what is left is 20 minus X plus 20 minus X oxygen plus XNO plus 10 plus X. So here X will cancel, it will be totally 50 only. That is what we had at initial stage after the first reaction also. So what is he saying? Since the process is done in a particular condition, the volume percentage is given. But a process is at a constant pressure and temperature, volume is always directly proportional to moles. Means your volume percentage should be nothing but mole percentage. So what is mole percentage is of O3? That is 10 plus X by 50 into 100 is equal to 50. Total moles are 50. 10 plus X moles of O3 is there. So this is 2. This is 25. So X is nothing but 15. Means here 10 moles of this is consumed. So that this energy becomes nothing but into 10 times. Because for every 1 mole of N2O5 reaction, this is 200 kilojoules of heat is absorbed, because it is a plus. So that it becomes 2000. But during this process, only 15 moles of this is consuming. 15 moles of this is consuming. That means into 15, which is nothing but 20 into 15 is nothing but minus 300. So that your overall energy will be 70. That's it. Done. So how much of that we have to calculate it? For that the percentage of ozone is given, but volume percentage is nothing but mole percentage. So we can determine that. So let us see this one, the last thing. The enthalpy changes, like what we actually do with the Hess law application and all that. So the enthalpy changes for the 2 moles of as liquid acetic acid. That is acetic acid is CH3, COOH, liquid is converting into CH4 gas plus CO2 gas. But resonance energies are given, bond energies are given. So what is the usual calculations is? So the CO2 energy, how much? Everything that we determine. So what is the total enthalpy change of this process? Total enthalpy change of this process will be nothing but actually total enthalpy change of this process is the enthalpy of vaporization, because you have to convert acetic acid, first liquid acetic acid into gaseous acetic acid, then only it undergoes decompositions where the bonds are cleaving and forming, so that it is converting into CH4 gas plus CO2 gas. Clear? So that this process enthalpy change we know, that is it is 50. But what is this process enthalpy changes? For any particular process, when all components are taken in the gaseous form, the enthalpy change of this process is actually is nothing but the bond energy, means directly I am just trying, bond energy of reactants minus bond energies of products. So when you use bond energies, when we use bond energies to determine the enthalpy changes of the process, we can determine through the bond energy of reactant minus bond energies of products. Means what energies exist in this? That is reactants. What is the bonds? There is 3 CH bonds, 1 CC bond, a C double bond O, 1 single bond CO, 1 OH bond. What is in this? There are 4 CH bonds and C double bond. Clear? So we can use these energy values to calculate. So already the bond enthalpy of CH is given, C single bond O is given. So O double bond O, that is we use, let us say maybe bond energies, enthalpy of formations if we use, and CC bond energy, that is also required for us, OH bond energy, C double bond O bond energy. So all that we can use and calculate. Clear? So this resonance energies anyhow I think is not enough useful for us. So let us say directly we can calculate now for the 2 moles. So only calculate this, multiply with 2, that is what you get enthalpy change for this process. Okay. So this is only again only the calculations whatever we require. So here the enthalpy change is directly given for us, that we can take, but enthalpy change of this directly you can use from this. If you add these two, then you will get the net enthalpy change for the process. Clear? Because heat of formations are not given, so there is no need of using the resonance energies at this stage I think. So directly we can use the bond and enthalpies, then we can calculate it. Done? So that we end with this here, and we'll see you in the next session. Thank you.